So that means that this session is a little bit longer than usual, so please don't get up after the third presentation. There will be a fourth. All right, so the first one is from the National Taiwan University. It will be presented by two students, Chung Te Lai, or Ted for short, and Johan Chen, or Tiffany. Ted is a graduate student working with Professor Polly Huang, and Tiffany just finished her undergraduate studies. She actually won Google's Anita Borg Award this year, and she's on the market for graduate studies. All right, so please take it away.
Got it. So thanks for the introduction, and good morning everyone. My name is Ted, and we are very happy to present our project. It's called PipeProbe, a mobile sensor droplet for mapping a hidden pipeline. So the idea of this project is that since the water pipeline are hidden inside the wall, it is invisible to us. So how do we use voice sensor technology to make a hidden water pipeline? And this is joint work with my left hand Tiffany, and she will give the first part of the talk.
So hello, I'm Tiffany, and the first part, motivation. How serious is the water scarcity problem? As you can see from this map, the darker the region is, the more serious is its water shortage. And in the darkest place, the water is so insufficient that it will soon fail to support the ecosystem there. Since water is such a precious resource, proper monitoring and maintenance of the pipeline infrastructure that carries water to us is also very important. Unfortunately, many water pipelines are not properly monitored or maintained. This figure shows that leaking is one of the 5 major consumers of water at home. According to a recent survey, leakage accounts for nearly 15% of all residential water usage, and it is measured to be 35 liters per person per day. Put it on a relative scale, this amounts to 18 times of the water consumed by a person per day. So can digital technology help us monitor water pipeline infrastructure at home? At most residential buildings, water pipes are hidden behind walls or underneath floors, so it is very difficult to directly inspect water pipes for leakage. If you hire plumbers to fix leaking problems, and if your house is old and does not have the original diagram showing where are the water pipelines, plumbers usually have to knock down walls or dig holes under the floors to see the pipes and search for the leaking points. This is usually a good business for plumbers because they often charge us more by refilling back the holes they created. This motivates our work. Plumbers will say that leakage often occurs places where 2 tubes join together or at the turning points in the pipes. So if we can locate these turning points or even reconstruct the overall pipeline's layout, it becomes easy for plumbers to accurately guess and locate the leaking points. We developed the PipeProbe system. It's a mobile sensing capsule. When it is inserted inside flowing pipes, it will gather sensor data to map the 3D spatial topology of water pipelines. Besides, instead of using single point or multi-point sensing as done in the previous related work, we adopt a mobile sensing approach and observe the pipes from within the pipes. This approach gives a more direct and precise detail of the pipeline's condition. The mobile sensing is also energy efficient. Its movement does not require additional motor. It simply leverages the natural water flow to propel its movement. Here's what the PipeProbe looks like. It's a spherical shaped capsule with a tail attached to it. It contains the following hardware components. The Eco Mode is made from Professor Pei Chao's team at UC Irvine. It's a low power and wireless sensor mode. It's small and weighs only 3 grams, including battery. It also has a radio and 3-axis accelerometer. There are 2 sensors attached to the Eco Mode. The pressure sensor exposed outside of the casing is to measure the pipe's water pressure, given less than 5 microamp operating current. There is also a gyroscope inside of the casing, which is used to measure the yaw or z-axis rotation angle of the capsule when it is making a horizontal turn in the pipes. So let's see how to use the PipeProbe to map the 3D pipeline layout. First, drop the PipeProbe into the main water inlet of a home. When an outlet such as a faucet is open, it generates a natural water flow. The PipeProbe behaves just like a water droplet and flows inside these pipe segments that connect the inlet to the outlet. While it is flowing inside these pipe segments, it will collect sensor readings from the pressure and gyro sensor. When it flows out of a water droplet, we will analyze the sensed pressure and rotation angle reading to reconstruct the pipeline layout. A typical home usually has one single inlet and many faucets and outlets. In other words, pipes form a distribution network with a tree-like branch or fork points. To sense a different path from the fork points, we can open another water outlet, drop the PipeProbe into the inlet, and map out the fork path. In other words, by turning on and off each and every water outlet and repeatedly insert the PipeProbe will traverse all possible fork paths and collect the sensor readings. We can then map the entire pipeline layout of the pipeline network. Let's see a video of how PipeProbe flows in the water pipes. The two windows show the sensor readings. The right one is the gyroscope graph and the left one is the pressure graph. The PipeProbe flows in the pipes with the water current and behaves just like a water droplet. When it makes a downturn on the vertical plane, the water pressure increases linearly with its depth. And when it travels on the horizontal plane, the water pressure stays constant. As it makes a left turn on the horizontal plane, the gyro gives a positive pulse. When it makes a right turn, the gyro gives a negative pulse. So here comes another right turn and a negative pulse. And then another left turn, a positive pulse. So how do we use the sensed pressure and rotation angle readings to map the 3D layout of the pipes traversed by the PipeProbe capsule? This is what the layout mapping algorithm does. To explain the layout mapping algorithm, I use a pipeline example here. The pipeline starts from an inlet and ends at the outlet. The pipeline structure between these 2 points is composed by multiple red horizontal layers, interconnected by green vertical tubes. And the problem formulation is that given the starting and ending position of the pipeline, how to locate each of the tubes traversed by the PipeProbe capsule. That is, to estimate each tube length, the position of each tube's interconnecting points, and join them up tube by tube, such that the starting position of the first tube is the inlet location, and the ending position of the last tube is the outlet location. And we make 2 assumptions here. The first one is that all the diameter of pipes is uniform. The other one is that at the interconnecting points, all turns are 90 degrees. This is reasonable because at most plumbing stores, you can often buy pipe joints only with 90 degrees turning angle. The layout mapping algorithm adopts the divide and conquer approach, and it has 3 phases: divide, conquer, and merge. In the divide phase, we'll partition pipes into vertical tubes and horizontal layers. In the conquer phase, we'll apply one method for mapping the vertical tube and another method for mapping the horizontal layers. In the merge phase, we'll connect or join the locations of the 2 parts together to form the overall 3D pipeline layout. And I'm going to explain each of the phases in detail as follows. First phase, divide, partition pipes into 2 parts. To separate them, we'll detect the turning points where the PipeProbe makes a vertical to horizontal change. For example, given a structure like this, when PipeProbe travels down vertically, the water pressure increases with its depth. When it travels on the horizontal plane, the water pressure stays constant. Therefore, by detecting the turning points where the PipeProbe switches to the horizontal plane, we can separate the pipeline layout. After separating them into 2 parts, we'll apply one method for vertical tube and another for horizontal layers. For vertical tubes, we'll estimate their tube length. For example, given a vertical tube like this, when PipeProbe travels downward, the water pressure increases linearly with its depth. Then, according to water pressure principle, the height of the tube can be determined by the water pressure difference between the 2 ends of the tube. Therefore, we can estimate the vertical tube length. To map horizontal layers, we'll first detect turns on it and estimate their tube length. To detect the turns, we'll use the rotation angle readings given from the gyroscope. For example, as PipeProbe travels on the horizontal plane, if it makes a 90-degree left turn, the rotation angle will give a positive 90-degree change. As it makes a 90-degree right turn, the rotation angle will give a negative 90-degree change. Therefore, by examining the rotation angle graph, we can detect turns on the horizontal planes. After detecting the turns, we have the starting and ending